Hello everyone, hope you all are doing good. So we will today discuss about first law of thermodynamics and hope you all have watched my previous lectures which is basically upon uh, basic concepts and fundamentals of thermodynamics, and if you haven't gone through it I would request you to go through the I button that is given on the screen. So let's start. Let's start by basic definition. According to first law of thermodynamics, energy can neither be created nor be destroyed, but it can be converted from one form to another form. So this basically simply says conservation of energy, like it cannot be created nor be destroyed, but only can be transferred. So yeah, so here you can see the closed integral of the heat or energy is equals to the closed integral of uh, work. So closed integral here means cyclic integral, means it is over a cycle. Like it should not be open for any process, otherwise it will not satisfy this equation. Here I have written it is applicable both for reversible as well as irreversible processes. And yeah, so it is applicable for only cyclic processes as I have mentioned, and not applicable for single process that they are its drawback. So from first law of thermodynamics, we can deduce some conclusions that we will discuss. So first is heat transfer is a path function. We can derive it in the following method, like Q1A, that is Q1A2, this path, to P1, then going to this path. So this is a cyclic process, and as I have told you earlier that for a cyclic process, closed integral or cyclic integral of Q is equals to cyclic integral of work. So here it is simply given this, and again for another cycle, that is 1A2, this is same, but returning cycle is 2C1, that is this. So we have equated it with the work, cyclic integral of work, and we have basically now subtracted the equation B from equation A, and we get this equation. So after that, we know that uh, it is a PV diagram, PV graph. So as we know that the work is the area under the PV diagram above the volume axis. So this will be the work for 2CB, right? So as we know that for like A1A, 2B1, 2B1 and 2C1 are two different paths. So they will have different work because the area is different. This is the difference between their work, this area. So this can be put in this equation number C, and we will get Q 2B1 2B1 and minus Q2C1 2C1 will also not equals to 0. It implies that heat transfer is a path function, means it is dependent on the path. And another conclusion we deduced from the first law of thermodynamics is energy is a property or a point function. So we will again use this equation C, and this equation C is written here, and we will just shuffle them. This will go to this side, and this will go to this side, and after that we will be getting this as the equation, right? So this, they both are equal, and you can see that they both have different path, 2B1 and 2C1. So what can you see from here? That irrespective of the path, the difference between the heat and work are same irrespective of the path. So what what this signify? This signify that the difference between these two properties is a is not a path function, is a point function. So this is basically that property that we represent by E, and this is a point function. And I have also told you in the previous video about this. And this can be expressed as the summation of kinetic, potential, internal energy. Internal energy is microscopic and other are macroscopic. The like microscopic is that molecular level, and for the time being we are neglecting the macroscopic forms of energy. Therefore, del E dE will be represented as du, and the equation of first law of thermodynamics can be stated as the following. So in this equation we can substitute del W by PdV, like work is PdV, and the condition for to substitute del W as PdV is the following. It should cross the boundary, like PdV work is definitely across the boundary because it is a boundary function, boundary phenomena, and also it is for the closed system. Yeah, it is for the closed system and the process is reversible. So we can replace PdV in the first law of thermodynamics. And yeah, so from these three condition we are putting it over here. So this equation is valid for closed system and it should be reversible process. And third is the energy of isolated system is constant. So basically for isolated system Q will be 0, work is 0 if it is isolated, then del dE comes out to be 0 and d equals to E final minus initial, therefore it will be constant. And let's discuss PMM1. PMM1 is basically a device that works on the violation of first law of thermodynamics. So its full form is perpetual motion machine of first kind. So it says that it is impossible to construct a device which produces work continuously without consuming any form of energy. So if you are producing work, then definitely you need some or the other form of energy for it to sustain. And PMM1 is a device that violates this, so it is not possible. So let's discuss about some expression of heat for different processes for constant volume. This is first law, and by this here V is constant, so dq V is constant, and this is the work for closed system, as like I have also mentioned it in my previous video. So dq will be du, and du we know is dq is mcv delta T, heat at constant volume, and u will become out as this because u is mcv delta T, is it is for always. Therefore here are some points to be noted. Internal energy is a function of temperature for only for ideal gas, like internal energy is only a function of temperature. This is U is internal energy, and this is applicable for all processes, as I've told you. It may be reversible, because you know that U is a point function, so it may not depend on which path you follow. It is just dependent on the initial and the final points, so it is applicable for reversible as well as irreversible processes. And let's discuss new term enthalpy. It represents the total heat content of the system, and it is basically H is represents all the type of energy that a system has. Total heat content, like, or you can say the heat content, like U is the internal energy or microscopic form of energy, P is the flow work or flow energy, and its unit is, since it is energy, so joule, and these are other another expressions for it to express. Let's discuss about specific enthalpy. So when enthalpy is divided by mass, it becomes per unit mass enthalpy. So this is another representation of that, and this is quite important to us because dividing it by mass makes this property as intensive. So and we know that intensive property are quite easier to discuss, and you can analyze this by doing certain numericals. And in this, PV represents the flow work, like amount of work required to displace out or into the control volume, that is flow work. And here you can see the some representation of that. Control mass is closed system, like we work on mass when it is like closed system, and we work on control volume when it is open system. This also I have discussed in my previous video. Okay, surface, this is like control volume or control surface, same things. Yeah. Case one was constant volume. Another case is constant pressure. So dq is by first law of thermodynamics. P is constant. So dq, like this p can go inside, because if you know that p is constant, it can come out later. So writing pdv or d of pv are the same thing. And after that we can insert this also inside this, and we get this, and this is it none other than enthalpy. So dq will be dh for constant process, and like uh, dq is actually this, because dh is mcp delta t. So heat at constant pressure is equals to dh, and dh is equals to mcp delta t. This is also for applicable for all processes, because this is a property and it depends only on points, not the parts. Yeah, same thing. For ideal gas, it is only function of temperature, but in other things like real gas, some other parameters may come into picture. But let's now limit ourselves to ideal gas only. Third is constant temperature. Same, du will be zero, because du, as we get earlier results as mcv delta t, and dt is zero, therefore d will be equals to zero, and dq will be equals to dw. This is basically representation of inexact differential, or the path functions. And for isothermal processes, we have already found out the work to be this, so heat will be this. Case 4 for adiabatic processes. Adiabatic processes, there is when there is no heat interaction between the system and the surrounding. Its example are insulated tank or thermoflask, where you keep your water in winters to be hot for a longer time. Yes, there is one question. Prove that there is no heat interaction in adiabatic processes. So for adiabatic processes, we need to prove that there is no heat interaction in this process. So let's prove it. Here are some basic relations. Cp and Cv equals to R. R is universal gas constant, and gamma is adiabatic index, and Cv and Cp uh, are represented as relation with R and gamma. dq will be equals to du plus pdv by first law of thermodynamics, and du is mcv delta t plus work done, or pdv for closed system, is represented here. This I have discussed in my previous video. This is nothing but the work. So work for the adiabatic process, and here PV equals to MRT. Written in this form, and CV is written in the form of R upon gamma minus 1 from here, and adding both this term tend lead us to making d equals to 0. That is for adiabatic process. There is no heat interaction. So we have proved this. One more question is here: prove that PV gamma, PV is to power gamma is equals to constant for reversible adiabatic processes. So more or less the process is same. So I leave this question to you. Like I will be providing all these notes in my description. If you found any doubt or any query, you may write in the description, or I will provide my email ID in the description. You can mail me, or you can ask for some explanation. I will give it in my other video. Same type of question is here. You all can see this PDF and try to do these questions. These are uh, some conceptual questions, mostly same. Case 5, like we discussed in adiabatic process, heat for adiabatic process, same is for polytropic process, just gamma is replaced by N. And I have told you in my previous video that N is between 1 and gamma. So this is quite important point. You need to remember this. And same process is there. And Q, you will get some like adiabatic, just some modifications are there, and it is quite easy, so you can read this. Here we have also found the specific heat for polytropic process. So this is dq. We have found it here. Here like it is expanded here, w close is expanded here, and this is the other term, right? So and dq is written as MC delta T. C is for polytropic process, and all the terms will go here, and C polytropic can be found out. This result, as I've told you, gamma n is always less than gamma but greater than 1. One more important relation, Mayer relation, we have used it earlier. Cp minus Cv equals to R. Here it is a proof of Mayer's equation. So dH equals to mCp delta T. These both are results from the previous slides. So dH equals to du plus d of PV. That is du plus MRT. PV equals to MRT, ideal gas equation. And mCp delta T, that is dH. mCp delta T plus MR delta T. Delta T, delta T, delta T all will be cancelled. And M M will be cancelled. Cp minus Cv will go here. Cp minus Cv equals to R. This is the proof of Mayer's equation. Some important points regarding heat and work. Both are path function. We have proved this earlier. Exact inexact differential, because path function, they are path function, therefore they are inexact differential. Both are boundary phenomena. We have discussed this in detail in my previous video. And inexact differential, you can see it like in this way. All the things that are like they have, if they go from one point to another point, and their integral might differ in uh, just because of the path you are taking, irrespective of the points will be same. Initial point will be same, point number two or the final point will be same, and their integral comes out to be different by taking different paths. So then it will be called as inexact differential. For example, this is point 1, this is point 2, You go from here to here, you go from here to here. Suppose this is P, this is V, then this will be the area of the path for this one, but the points are same. Keep this in mind. And this is the area of another one. So this is the net difference, right? So both the integrals will be different, but they have same limits. So if this happens, then this is a inexact differential. Let's move on now. Here are some differences about heat and work. Like all the form of interaction are work other than energy interaction due to temperature. Uh, uh, Everything where energy transfer happens, because like when the driving force is the temperature, then it is heat. Other than this, all things, all energy interactions are considered to be work. A and the PV provide the work interaction and TS provides heat interaction. These both graphs I have discussed in my previous video, that is basic concepts of thermodynamics. Here are some important points that you should consider because they might ask in exam. These are quite important. So, while finding work on PV or TS diagram, when the cycle is in continuous, sorry, clockwise direction, then the work is reducing. Means work is positive, like Carnot, Otto, Rankine. And when they are in anti-clockwise direction, then the work is negative because work done is on the system, like reverse Carnot, reverse Brayton cycle. Here is one question, let's discuss it. A spherical balloon of 1 meter diameter contains gas at 150 kPa. Initially, the gas inside the balloon is filled until the pressure reaches 450 kPa. During the process of heating, the pressure of gas inside the balloon is proportional to the cube of the diameter. This is important. Then find out the work done by the gas inside the balloon. We need to find the work done. So given diameter, initial pressure, final pressure, this relation is important. We need to find out work. So from this relation, keeping K is constant of proportionality. So P equals to K dQ, and we know this is a closed system. So for W equals to P dV, and volume for sphere is this, or can be written as this. And so dV, if V equals to this, then dV will equals to this. And uh, from initial condition, we will find this K. So this K is this, and we know P2, so we can find D2 directly, as we know both D1 and D2, and work as a function of diameter. So we have K, we have work as a function of diameter, and we have both the limits. We can directly find out the work done just by simple integration. So this is simple to solve. Yeah, here are some more questions that are quite similar to this. So you can go through it and just let me know in the comments if you have any doubt. I will clear it in the next video if it is required. So let's discuss about open system. First law of thermodynamics for open system. So steady flow energy equation. Basically, in open system, we will consider control volume rather than control mass, because like the flow will be coming in and going out steadily. Here we were discussing about steady flow. So steady flow means properties does not vary with respect to time. They are constantly coming and going. So properties are constant, and here are properties that in specific enthalpy, kinetic energy, potential energy. All these are in specific because we need to have intensive properties that are not dependent upon the volume and mass. Uh, Flow work, velocity, return, potential head, datum head or potential head, whatever you say, heat work, mass. So this from here, this side there, mass is coming, going, and this dotted line represents the control volume. So by energy conservation or first law, U1 plus P1, PV1, that is flow work, kinetic energy, potential energy, plus U1 makes in energy into energy, and P1 V1 flow work, Q is the heat given, and this is work output. Rest things are same the right side also, and after doing some manipulations, we get this as our equation, and yes, so this is our final equation. This is basically simple. We are just doing conserving the energy. Uh, It is quite simple case because it is for a steady flow. We do not need to consider the change in mass. So only energy conservation equation is important for this question. Some special cases for open system or steady flow open systems are nozzle. Nozzle is a mechanical device. It is one of the most important device from in mechanical engineering. It basically increases the velocity or kinetic energy of the fluid. It has also an exception that when the energy is more than the energy of the sound, then at that time it becomes supersonic. So at that time, this nozzle works as a diffuser. Diffuser we will discuss next here. So, but we will not go in that case because here it is not of much importance. So, we will consider nozzle as just a device to increase kinetic or velocity, kinetic energy or velocity at the expense of pressure energy. Because energy can neither be created from or nor be destroyed from any other thing. Therefore, some need compromise is required. So, this energy compromisation is done from pressure energy. So simply neglecting potential energy, taking it to be insulated, no work interaction, neglecting initial velocity, then we see the nozzle. So H1 equals to H2 plus kinetic energy because we are like here the kinetic energy term is not there because we are considering V2 very greater than V1. Like velocity is very low for at the inlet of the nozzle. So here from here we can find C2. Here we are dividing by 1000 because these H1 and H2 are in kilojoule per kg. Kilojoule per kg. So C2 will be equals to this. You can simply learn this formula because it might like they ask in exams in competitive exams. So it can be directly used to find the velocity at the outlet of the nozzle. Unlike the nozzle diffuser, just do the opposite thing. It decreases the velocity. Formula will be same because the concept is same. Another example is turbine. Turbine is a device by which we use the kinetic energy or uh, transferred from the working fluid to the rotor. Like energy is transferred from the working fluid to the rotor, and this energy is basically kinetic energy because kinetic energy is responsible to rotate the rotors of the turbine, which then generates energy, electrical energy through the generator. Decrease in pressure. So pressure is decreased in this process. In this case, turbine, the value of net work output is positive because work is done by the system. Kinetic energy changes and potential energy changes are also neglected. Like here in turbine, what happens? The pressure is reduced. So these are some assumptions because they can be ignored to consider while making doing some experiment because they are not of much importance. And one more important assumption is it is value insulated. So using steady flow energy equation H1 plus K1, this equation we have wrote earlier, and neglecting like considering all the things here, we get this equation and again work as this. Like you can see here, we get the velocity by these things. So yeah, and this is the schematic of turbine and the compressor. Just opposite things. At turbine expansion happens and at compressor compression happens. Compressor and pumps. Both are devised for like rotor energy to like converts energy from rotor to the working fluid. Just the difference is compressor is used to increase both pressure and temperature because it is used for fluid like gaseous phase, whereas pump is for increasing the pressure of the working fluid and generally liquid because liquid is uh, quite difficult to compress, so its temperature does not vary. Therefore, it is only for pressure increasing. Formula is same as for turbine. In boiler evaporator, both are type of a heat exchanger, uh, which in which heat is absorbed by the working fluid at the constant pressure. In both the things, heat is absorbed at constant pressure. Energy again are neglected. Work interaction is neglected. So putting steady flow energy equation and neglecting things and considering the assumptions, we get this equation. Condenser is another device which basically rejects the heat by the working fluid at constant pressure. Again, this formula. So this is consistently used. So you need to at least derive them once and remember this for long. Throttling. Throttling is used in our refrigerators. So this process is basically isothalpic. And again, these assumptions: no heat, no work, no kinetic energy, no potential energy, and applying the statistical equation, and we get this result. So isothalpic process, as I told you, same enthalpy at the outlet at the inlet, decrease in pressure, expansion, irreversible. This process is irreversible adiabatic process. So as I've told you in my previous lecture, this is irreversible and adiabatic. So it cannot be isoentropic. Entropy increases because for isoentropic it need to be reversible. Free expansion or unrestrained expansion against vacuum, like there is no pressure outside the piston. Suppose piston, taking example of piston, so it is against vacuum and it is irreversible process because inside is, suppose any pressure is there, may it be very small but it will be finite, so it is irreversible. Things are zero, work is zero, heat is zero, therefore this will be also zero and this will be also zero. Also termed as unrestrained air return. Let's take a question. Air temperature of 15 degrees Celsius passes through height at the velocity of air. Temperature air. This turbine, some velocity of 30 meter per second, expands until it reaches to air 50 degrees Celsius and all. So we have to find the rate of heat transfer to the air in heat exchanger in kilowatt. Power output from turbine. These assumptions. velocity at the exit of nozzle. So I would recommend you to just try it once on your own and then see the solution. So this is schematic. First, this is mentioned here, heat exchanger, then turbine, then nozzle. So what we will apply this equation one by one. So by applying it in the first phase, we these are not neglected, but kinetic energy will be same because velocity is 30 meter per second, 30 meter per second, and potential energy is neglected for the whole system. Okay, so these terms will be cancelled out, and work interaction is also zero. Therefore, Q you can find out just by this because uh, H has a formula MCP delta T or MCPT and delta T because H2 minus H1. So yeah, you can find out, and you know the m dot. M dot is 2 kg per second. So this is multiplied by m dot 2 kg per second to find power. Uh, then we have to find the output of the turbine assuming no heat loss. So turbine's output. Just apply the steady state flow equation again, steady flow energy equation again to this process from 2 to 3. This is the process. You know everything. Uh you need to find just the power output, right? So by this equation, you can find the power work and multiply by m dot. This is the power. And if for finding the third thing, that is velocity at the exit of nozzle, you just need to do like again apply the same equation and you can find C4. So this is H velocity, other things are neglected, and C4 can be found. Similarly, as we have discussed for steady, then there are also equations for unsteady flow. Unsteady flow in which like properties are varied, property varies with time. So mass flow rate at the inlet is different, exit is different. Therefore, with certain interval of time, the mass that is inside the control volume is will be also be different. So here two principles are used: conservation of mass, conservation of energy, initial mass, uh, uh, and like entering mass at the control volume, inside control volume mass initial, final mass inside control volume, mass at the outlet or coming out of the control volumes. This is mass conservation. dm by dt equals to m dot I minus m dot t. Entering, leaving. This will be the change in mass. So this can be represented as this. So this will be equation 1. Similarly, energy equation. This is the difference. We are taking here difference. So change in energy with respect to time in the control volume plus 2. This is because of entry. This is entering lost kinetic energy of entering fluid, potential energy of entering fluid. Similarly, here exit, and some Q is there, W is there. Then on resolving, neglecting the things like potential and kinetic energies. So you got this equation number 3. So here we are neglecting the variation of enthalpy at the inlet and outlet with respect to time. So this can be neglected because it does not have much influence. Like the enthalpy does not change much in this. Okay, so this can be here. How this becomes U, because as you know, E is summation of kinetic, this potential plus this internal energy, and we are neglecting kinetic and potential, therefore it becomes U. And later this equation is used here. So expanding this, we know that like this is expanded in two terms, right? This will be zero because enthalpy change is zero, because at the inlet enthalpy is constant, at the outlet enthalpy is constant. These two terms are zero. So what we are left with is these terms. So this becomes the unsteady flow energy equation for open system, and its application are like charging and discharging of a tank, because you know that while the inlet of the tank and the outlet of a tank, like the outlet is quite slower to take out the water from the tank outlet, and inlet is at high velocity, like inlet comes at a high velocity, and bottle filling process and all. You can also see more examples on internet. So hope you liked this lecture, and if you think that you have gained something, then I would request you to like, share, and subscribe this channel, and share it with your more friends, so that I get some motivation to make more videos. So let's meet in the next video. We'll be discussing about second law of thermodynamics and some of its practical applications and numerical.